are inserting the buffer. So it is defined. So buffer are in between the discrete domain. We are inserting the buffer means basically to increase the signal strength and the transition. So like there should not be any because we are seeing the congestion and like a voltage drop also in that region. So because of that, for this transition, we are using the buffer in between the like discrete domain and the voltage identifications. So like we can see in like in UPF or CPF, it is defined like create power domain PD top hyphen include scope. So what does it means like hyphen include scope means it is the top level like top power domain. So inside that some module will be there. So like let's say upper domain, the main domain have the VDD int. So inside that VDD int, a number of like power domains will be there. So number of power domains in the sense we are describing it in the element form. So that's why like here we can see the create power domain PD on like the name of the like domain and hyphen element. So element that name that power domain. So it is like A1 name. So basically here hyphen include scope is like the top notch power domain and like in between power domains like we are seeing the submodules power domain which are called as elements. So those names are like Aeon wrapper and PGD wrapper and something like Aeon and PGD both merged will be. So this is how we are defining the power domain in the UPF. And basically for the voltage array creation, so first what we will do means initial stage like we are creating the region, like in which region. First we will see the in which region we have to create the voltage array. So like in like that we are creating the region. So create region hyphen name and PD1 region. Hyphen react or debug we can give in Innovus. So it will give the coordinates. So for that like we are defining the region. So how we will define the region means like create this one for like I have like 4 power domains. So for 4 power domains we have to define like the regions. So and based upon that like we have to add those like cells on that region with the command like assign instance to the region. So add to region PD1 and PD2. How many like power domain will be there? Based upon that we have to do this one. Insert the cells into that those regions which we are defining initially. And like we have to define the power nets. So define power nets for the island. So we have to give the GNC connection for those. And like if we have the ESD in the region also, like we have to give the GNC. Why we're giving GNC means like because those are connected with the global VDDs. If we are not giving the GNC connection means like power will be mismatch in between the subdomains. That way we are giving the GNCs in between the those nets actually. So like PGP pin and like instance region and this one. So this is how we are giving the GNCs. And then like we are creating the voltage region. So like create voltage region is there. So whatever the power domain name and those coordinates will pick up from there and like power domain and ground. This is how we are defining the VI creations. And let's say here like low. These are the low power cells which are controlled by the PMU. So basically, PMU is nothing, nothing but it is the like power management unit for all those sub modules. Like you are seeing the power switch, multi-VDD, like it will control the because how it control means it has the control enable signal for each and every logics, each and every cells in the design. Like let's say for power switch it has some like enable pin, like for level shifter isolation. Through that enable pin it will control in the design to interrupt the power. Like for us like human brain, like for human like brain is the PMU because why it gives the signal to the heart that for example like if you want to go and like if you ride the bike speeds in like 150 km/h, so like brain hits the signal to the heart that it might get the accident. So because of that like this is how like design like PMU hits the signal to the power. So basically it will control the units with the help of like enables signals. So this is how the power management, like power management supplies the manage the powers to each and every logics which are independent of the like voltage domains. Let's say PD1, VDD1, PD2, PD2. Like this is how it will supply the power management unit to each and every cells in the design. Like moving to isolation cells. So like why isolation cells come into picture first? So like in the initial phase, I told like because of the low power in the design, because of the from top level. So they are deciding the they are going for the like different blocks operates in the different frequency and like different domains. Like some blocks operates in the like BLD one, some are switchable, some are always on. Like example, a CPU, GPU, which are working for the high frequency chips. So like for those like which are working for the low power domains basically. So sorry, high power domains like BLD one, BLD, and like some are going in low power domain. Only one single BLD is enough. So basically, we are going for multi-voltage means like we can see that more than two VDDs, and for elevation like we can say the one VDD. So based upon that, we are initiating the design. So and because all the block does not require the same supply set. So because same supply set in the same voltage does not require all the blocks. So different voltage required for different blocks. So that's why we are moving to the multi-voltage. So here coming the because of that the concept coming because of low power. Here we can see the isolation cells. So actually basically what is isolation cell means? So isolation cells are like the it is low power cells in the design. So it is like it's placing in between like on domain and off domain. So here we can see the image. One is always in domain and inside always in domain there's a power gated domain. So like power gated domain is there. So in between power gated domain, what happens is like power gated domain is if it is off, then we have to like PMU is there. Initially I told PMU is the like control unit. So and here is the like where we inserting the isolation cells. Like here is the PMU. So from PMU it is passing the like NOT gate is there. So initially we are giving 0, and if we are giving 0 to the NOT gate, so its output will be 1. So 1 is going to the OR gate. So OR gate. So for OR gate, if it is if we are giving 0 means it is normal operation. If we are giving 1 means it is a clamp operation. So it clamp the signal. It clamp the signal and pass to the another voltage domain. This is how it works actually. So and if you are giving 0 to the AND gate, clamp 0 means like it is clamping a signal for the AND gate, and 1 means normal signal for the AND gate. So the and both AND and NOR we are using in the design so-called isolation cells. So if we are not using isolation cell means what happens if we are not using isolation cell means like between a signal will be there. So whatever the domain power gated domain will be there, passes the signal and it will be like it will off. So there will be a unknown signals passing to the known allocation domain. So like which cause the metastable states in the design are like overcurrent. So overcurrent are like you can say uh, like unknown values, whatever might be. So it caused the design failure because it is unknown to the like next stage. So because of that, we are using the isolation cell, and overcurrent is basically like high current, which helps the cells to initiate the like another cells to goes for the high current actually. It hits the current line actually. So this is what called the overcurrent. Like this how like you can see the like floating output will be there, and where we basically where we will connect the isolation cell means there will be a power gated block, and power gate block has the output pin. There will be output pin for the power gate cell. In that output pin, we will insert the like we will insert the isolation enable like pin, and we'll connect and like basically we are this. And if we are without giving the like isolation cell, the signal will be like floatings. So when we apply the isolation cell, the signal will be in constant form. It will known the value like whatever the previous state value is there, so it will be known. So and like the command is like basically how it define means like set isolation cells, like in which domain we are doing this one, and like isolation power is for like net BTD low and ground. And like clamp is 1 means we are using the OR gate. If your clamp value is 1 means we are using the OR gate to clamp the signal. An element means like that is PGD wrapper. That's how like we are defining the in UPF file. And coming to retention set. So retention logic is basically here you can like it helps to retain the data. Means whatever the data store value will be there. So whatever the data in the like power of domain will be there. So it will what it will means. Here we will have the flip flop and latches in the retention. It consists of flip flop and latches. Contain the flip flop and latch in the retention. So in latch, one is like in ready on you can see save. Because why it is always on means like whenever the it will save the data before that block is powered off. Whichever domain is there, if domain is like off, means before off only it will save the data and it will restore the data and it will fetch to the next power domain. Or like it will fetch the data to the MLS. So like where it place means like it place between the like will place in the like near the off domain. So like will we're placing the near the off domain and the signal will fetch and it will save in the latch and it will reach. So this is how it will work in retention cell. So basic work of this retention cell is like to save the data before the power loss. To save the data before the power loss and restore it to the another domain. These are retention cell work. It is a level shifter. So level shifter means like when we are using the multi-voltage domain. So like we are when we are using the multi-voltage domain, like if we are converting the low domain to high or high domain to high to low voltage and low to high voltage, we are using the level shifter. So level shifter are basically placed in the core and IO regions. So how it is placed in the IO region means like from one block to another block. So there will be low voltage to high voltage because in core we require the high voltage to operate the cell or like depends upon the like design like how we can like if it in core requires the low voltage then we are using the in IO region through pad it comes level shifter. So through around all the like in all the region of core area we are using the like in all the IO core we are using the, like level shifters. So because like our sub modules we don't know like what voltage coming from the outside lens. So depend upon the like regions requirement we are placing the level shifters like from high to low and low to high. So from inside for example let's consider we require the high voltage in the core area. So what we do means like from outside to inside we are placing the level shifter. We are placing the level shifter of like high to low to high. Then we are getting the high voltage in the core area and like from core to IO outside region we are having the like low to high, high to low and low to high in the through the pad goes and in between the core region how it will place means like in between the core region like uh, between the cells like between the cells and like if it is like a interface level or something so here we can say. So because of this figure, like here we can see like power domain one, top, PDY and PDZ is there. So these are the level shifter is you can see here. Low, it is placing in between the periphery region, that is boundary region between the two power domains, PDX and PDZ. So this is how we are like let's say like PDX voltage is low. In like PDZ region, we require higher voltage. So here we are placing the low to high level shifter. And like from top also like in isolation cell also like we can place in the boundary regions in between the like power domains and the boundary. So level shifter like it works and it is like for the whole top module we can place like this and for like sub blocks between the standard cells how we place it, like PD1, PD2 and PD3, PD4. So like low to high and high to low. In this way we are placing the this for one block only. Let's say design top. This top block only we consider here, and like we are placing the low to high level splitter in between the standard cells. And like types of level splitter, like you can say like low to high or high to low or bidirectional. Bidirectional are basically used for the like interfacing the signal between like if one signal require two voltage at a time or like two domains. So based upon that, we are using bidirectional. Yeah, power switch. So like power switch, we can say like power switch are the basically we can say power switch are like it's also called GDHs, global distribution header switch. So we are using the like why basically we are using the header only. So like power switch are of two types. One is like header and one is footer. So why we are using the like header basically not footer because like in multi-voltage domain we require power switch. So like what even means in multi-voltage domain. So like we have to control the major supply power VDD supply power which is VDD. So to control the VDD we are using the global distribution header switch. That is the reason we are using the GTHs. We can say the power switch name has a like two types actually. One is header and footer, but we are using the GTH mostly. So global distribution header switch. So like it is placing like while we are placing the power switch, it will help to avoid the ingress current and the instantaneous damage. So this how like it will help and like basically it will place in the decision fusion. So in the design, it will spread all over the design. It will in my case, like in my block, like four power domains are there. So in between power domains only, like GDHs are there. And like offset power domain, it's not there because one of my block is like always block is there. So and like in those power domains, like GDHs cells are there because based upon the hierarchy. So like let's say BD MX int is there and BD CX int is there. So for BD MX int, like what we do means like those hierarchy cells which are depending upon the those hierarchy and belongs to that power domains cells are placed in the VDD MX int and similarly for CX power domain which are belongs to that are placing into the CX domain GTS cells and outside is not there because why not there means like there is a one of my blocks always on so it does not require the power switches. That's the reason. And like for this we have to before placing the power switch we have to check the like whatever the pitch value offset value and the orientation of the power switches in the like we have to get one file power switch file is there in like while we're using so we have to check and we can design also like I have checked the power switch distance between those GTS cells like it is like 7 micron for one and another is like for 5 micron.
Don't know what happened. Yeah.
5 microns. So based upon that one is going on. So like when I will check, so first we have to see the pitch. What is the pitch value? Pitch means like center to center distance between the power cells. Sorry, power switch. And like offset, what is the offset value? All those are defined in the like UPF only. Like we have to see like we have to extract from the UPF file and like we have to use in one overhead files and we have to see like what is the pitch and what is the pitch and what is the offset value. So whatever and major thing is like whatever we are defining the pitch in the that file and we are doing the rechecking in the design so like if it is match or not like whatever let's say we define the pitch value is 7.5 for one of my like power source and there is like for a vertical direction it is 7.5 and for horizontal direction it is like 3.5 so we have to initiate in the design that like it is like verifying one. So I have checked both the times, like it's verified actually for horizontally and vertically. It is like same. Whatever we are defining, it is same as the previous one in the whatever we are defining design. So this is how like we have to place the power switch. Power switches are like in a different design fashion. And so like if my thing is like let's say if power switch chaining are break let's say in the design like if power switch chaining is like a break in the design so what we'll do is like power switch has the four pins power switch has the four pins those called as like enable few and enable reset acknowledge few and acknowledge reset so what happen means like we have to connect those like enable few should connect with the enable few signal and enable reset should be connected with the enable reset. If we are doing so, then power switch chaining will be if power switch chaining is break, then we can initiate reback the power chaining like with the help of those pins by connecting. Like enable few should be connected with the enable few. So these are the control signal which are defined in the UPF. So this is the power switch pin, and because of this, if power switch chaining is break, like for me case in like in PDN review, like all like GDS chaining is perfectly like coverage, like GDS coverage is fully zero actually. It should show 100% the design, but for me it's like zero. So what I did means like I should reconnect, like what I did means like I should reconnect the enable few signal with the enable few, like we can say mapping. So we are doing the mapping as compared with the help of UPF file. So whatever we are defining the UPF file, we are doing the mapping. Enable few should be mapped with enable few, and enable should be enable few. And in between again, like for me, like I cannot see the like enable few signal to the enable few, because one of my like one of the cells are sitting in between those. So like we cannot reach the output. So what it means, so again feedback has come, and like what I did is I asked them like my lead, and like he told like we can leave those cells. Some of the cells are sitting in between, like we can say some it will come in between the power mux will become, or something will become in between mux will come, or something will come. So he told me to not delete those cells, let it be, because I'm not seeing the output from input. We have to see like in the design the coverage is 100% only, but not seeing the fully actually. That's why. So these are the things actually. So combination of header and footer switch like consider as a power switch. So like here I have one questions like how to calculate the number of power switch in the design. So how we can calculate it? So like with the help of power switch, what we can do means we can reduce the leakage power by cutting the flow of VLD and VSS. Like when the block are ideals, like not in the active state, so we can like cut the power in those actually. So we can do it. Like how to calculate the power switch in the design means like we are calculating the power switch in the design depend upon the like area. First, we will see the area and the like power domains. So how many power domains are in the design? Based upon that, and like what we do is like area. Depend upon those two things, we are deciding the power switch. Like how many power switch we are calculating in the design. Coming to next slide here. So what is the difference between the GTHS cells and the overlay cell? So additionally to like GDHS is the global distribution header switch. Like why we are considering only the GDHS means like in multi-voltage domain, multiple VDD will be there. So we have to control the VDD power supply to reduce the dynamic power distribution or dynamic error drop. So for this we are using the GDHS cell. And like what is overlay cell? So I'll show you the picture one. So this is the GDHS cell and this is the overlay cell. So like these are like overlaying. Overlay means merged. Overlay meaning in the sense it's merged. So how it is merged means basically the power switch and overlay. So what is the use of overlay cell means like it helps to deliver the power to the GTHs. How? Like GTHs cell have the like pin which are very thin, and it can deliver the high current in the like power grid. So because of that reason, what overlay cell means like overlay cell have the like pin shape. Let's say the major differences between the GDHS and the overlay is GDHS cell have the transistor, but overlay cell doesn't have the transistor. And like the major differences, like there is no transistor in the overlay cell, and the like there is no like delivering power delivering factor. So the like overlay cell, how it helps in the power delivery means like overlay cell have the wide density of metal straps and the VI redundancy. Through that, like and it have the pin shape like BDD, BSS, and BDD AON, and like BDD power switch. So these have the pin name. Let's say. So how these are the pin name in the design. So pin name in the design. So like for that it will what will do means like and like all the power of this overlay cell are connected to the global power, global VLD, sorry, global VLD. So it will connect to global VLD, and those pin, whatever I told, whatever the pin of that overlay cell, it's mapped with the UPF, and based upon that, and it will it will supply and it will connect the those VLD are connected to the global VLDs, and it will map and it will supply the power to the power switch. because like overlay cell have the wide length of metal strips and via redundancy. Through that it can and also it have the low resistance but high current carrying capability. So and it helps the GDSs to like deliver more power, the power grid, and also it will helps to the DFM. DFM means like design manufacturing. This one for manufacturing, like it is like robustness. So all these things. And like coming to like how we will define the standard cells height means like this is the formula. So standard cell height can be defined as the like n fin. N fin comes from the fin plates. So number of rows can define into CPP. CPP means like contact polyphase. So how contact polyphase is defined is like CPP sets the unit is value for this one. And like coming to n fit rows, like how it defined means like how what does n fin tell how many pitch stacks, like how many pitch stacks from the height. So, mm, there, for example, let's consider there is a 7.5 track cell height is there in one design, and another design is like let's say a 9 track height cell height is there. So for that, what happens means like and basically CPP we are CPP we are using for the lower tech because in higher tech not not required because in lower tech mode like coming from like 753 in this end we are using the CPP because if the CPP value is low. If CPP value is low means like what happens means like cell are densely packed and the manufacturing issue will be there during manufacture issue will be there because since we back and we can see the more number of air drops and like routing issue will be there and all those things will be there. So these things is there. So in like let's consider like 7.5 track 7.5 track cell height is there. For that let's consider 7.5 into 32 CPP. Like I have considered 32 CPP in my design because like 32 CPP is the like good one, good price to go with the one in the design like for TN actually. So why it is used means because like there will be it will define the cell height basically. CPP define the cell height. So how many like this one. So whatever we are doing means 7.5 into 32, it come around 268 something micrometer. So this one is the our tall height of the cell, define the cell height. So it is different from the foundry actually, like how many CPP we have to use in our design based upon the technology node. So like shutdown logic are there. Like this is the like can we go for like clock gating. So clock gating is the like power optimization techniques to reduce the dynamic power distribution that is. So like it reduce the like because of clock gating we can reduce the unnecessary clock buffering and the power wastage. So there are two type of clock gating. So one is less free clock gating and one is less based clock gating, also known as ICS. So less free clock gating is there. So less free is the end based clock gating. So what is the clock? Clock signal is passing over there and is the gate delay. So this gate delay, like, because gate also have some number of internal delay. Because of that, like clock gated clock is getting the chop with the clock. So which causes the noise and delay in between those things, in between the clock and the like output. So clock has been chopped. So we can see the clock chopper or the glitches. Produce the glitch. So we are avoiding less free clock gating, and we are moving to like less base. So less base is like we can say the ICG. So this like we are using the low active signal in the sense like enable is like low. So this one. So here is the enable signal we are passing, and this is the clock and output Q. So how it means like every negative edge of the signal, it is the high. So here is the negative edge. So signal started high, and again in negative edge it got low, and like this step. So and the output is at the end of. So we are merging this one Q enable. So we are defining like output is passing through the like enable high when is the case. Yeah, here. So this one is here we cannot see any like clock glitches or any clock jump. So that's why we are considering the ICs. And coming to power gating, so like what is power gating? It's like it will help to reduce the leakage power actually in the design. So like here, like you can see total power is like power dissipation is a dynamic power plus steady. So in dynamic power, you can see the like switching power, internal power, and like circuit power. And in static, you can see the leakage power. So let's say dynamic power is there. So half of CV square. So whatever the theme is like VDD supply voltage square. So in multi voltage domain, how multi VDD how multi-VDD like helps to reduce the dynamic power means let's consider one of VDD has the 1.1 volt and one of VDD has the 0.8 volt. So when because of the calculation like equation, so half of CV square into F into activity factor. So what does activity factor means? Like activity factor is the average rate of switching of the signal. Average rate of the switching of the signal is called the activity factor. So VDD is very there. So in VDD, let's consider two VDDs there. One is 1.4 and one is 0.8. So let's consider 0.8 VDD. So whenever we are doing the 0.8 as a whole square, so it is like considering the 0.64 means into 100, 64%. 64% of the dynamic power has been like controlled by the with the help of this. So that's why like we are considering the multi-VDD options. And like internal power is like E into F time into activity factor. The formula for the internal power is like E into F into activity factor. And like static power is like I leakage power. So I equal to V leakage into I leakage. So these are like power gating is like two types of power gating are there. One is fine grain power gating and one is coarse grain power gating. So while we are using the fine grain technique, so fine grain are used for power gating on the like standard cells. Like indivisible. For indivisible purposes, we are using the fine grain purposes. That is for standard cells or any gates, which leads to like high isolation problem. Like we have to use a more gates, area issues will be there. So because of the issues, like, and one coarse grain. How we are implementing the power grid. So this is how we are implementing the power grid. One's PMOS and NMOS. Between this one, like this one is NMOS here, both like header and footer. And